A sub O is your original amount. Is that too loud? Yes. And A is the ending amount. Hard to get along with. Okay, try to make things lively. Not so boring. Okay, so A sub O will be O for original. Okay, so they're going to give you, it could be population, it could be carbon 14, because that's what we measure when we dig up bones, or we're trying to find how old the bones are. So there'll be an original amount of something, that's A sub O, and there'll be an ending amount of something. Please tell me everybody knows what E is. E is about 2.7. You'll never put anything in for E, guys. It's a value all by itself. All right? K is your rate, okay? K is your rate as already in decimal form. Okay? It's a rate already in decimal form. So let's say your rate of increase was 7%. Then that K would already be 0.07. Okay, it's your rate already in decimal form, and y'all bet y'all can guess what T stands for, because T always stands for this. Time. Okay, so this formula is used for everything in this section. It is called, should tell you what it's called, because in your directions it'll tell you to use the formula. It is called the sometimes it's called the growth model, and sometimes it's called the decay model. It depends on whether something is increasing, okay? So if something is increasing, they may ask you to write the equation for the growth model of the problem if something's increasing. Or if something is decreasing, then they may call it the decay model. But this is the formula that they're talking about. There's no other. If you're writing a formula, this is the formula that you're going to use. Some of the beginning formulas will be a little bit easier, and they'll give you the formula, and then there'll be some harder problems where you have to come up with your own growth model or your own decay model. Okay? So we're just going to start. We're going to work as many even problems as we can in the 30 minutes that we have left. So we're just going to start with number 2. I need you to be on page 469 because these are word problems. I can't write all the word problems up here. You need to be able to look at them. There's going to be some formulas that they give you. Now, if you have ever been that person that said, oh, I hate word problems and word problems hate me, and I'll just get everything else on the test right, and I'll just skip a few word problems if I have to. Well, guys, this test is half and half. It's 4-4 and it's 4-5. Okay? So that's not a good plan. Page 469. Okay? I had a not so good Algebra 1 teacher way back in like 1981. And back in the 80s, there weren't word problems in each section. So have y'all noticed how that might have changed over your years? How they always put word problems at the end of every section? Well, back when I went to high school, they just saved all the word problems for a giant chapter at the end. And I can remember my Algebra 1 teacher going, oh, that chapter's about word problems. We'll just skip it. Which was exciting at that time for me, but it didn't help me later on when I had to deal with it. So anyway, most textbooks will now embed those word problems in each content section that you do. Okay, so what do you see on page 459? What countries are they giving us formulas for? Okay, India, Iraq, Japan, and Russia. Above those equations, it says the exponential models describe the population of the indicated country, A, in millions. So if A comes out to be 5, it's not 5 people, it's 5 million people. So A is in millions. T is years after 2006. So T is the number of years after 2006. Use these models to solve the problems. Okay. Number 2 says, what was the population of Iraq in 2006? So this will be an easier problem because they've given you the equation already. So Iraq's equation is A is equal to 26.8 e to the 0.027 times t. So the original amount is 26.8. They've already put that in for you. And they've also put in the rate. The rate is that 0.027. I know that because t is still in the equation. Now let me talk to you about the k being positive and the k being negative. All right, this k value is positive. So guess what that means about the population? It's growing. Okay? It's growing because this number is positive. If the k were negative, then something would be decaying or decreasing. All right? So they want to know, what's the population of this country in 2006? Well, in 2006, what is the t value? In 2006, what is the t value? Is it 1? It's 0. Okay? In the directions for this set of problems, it says t is the number of years after 2006. So if you said t was 1, what year would it be? 2007. Okay? So all you have to do is take your little t as 0, go up into the equation, replace that t with a 0. I'm not going to rewrite it. And then you're going to have to multiply your k times your t and get 1 exponent. Well, that's easy because you're multiplying by 0. So all of that's going to go to what? 0. And I know you're not touching your calculator, although I hear calculator buttons out there. There is no reason to raise e to the 0 power because we know anything raised to the 0 power is 1. Okay? If you want to use your calculator, you can. Then you're going to go, oh, why did I do that? All right? A is in millions. So we're going to say 26.8 million. You're going to put your unit on your answer. Okay, or I'll take off a point for that. Make sure you put your unit on your answer. Now, once you get the hang of this, you may not have even worked out number 2 because you would realize that the 26.8 was the original amount. And that would have been in the year 2006 when t was 0. If you want to just work it out to make sure, that's always going to be your amount in the beginning year, whatever year this information has been collected. All right, let's go to number 4. 4 says, which country has a decreasing population? You can just look at the equations. Which country has a decreasing population? Russia. Why? It has a negative k. It says, by what percentage is the population of that country decreasing each year? So you can just take the k value. All right, it's negative 0.004, right? And move the decimal 2 places to the right. They want to know what percent. Okay, so that's going to be, it's not negative. You really just say it's 0.4% decrease. Okay, the negative means it's decrease. Percent is never negative. All right, it's never a negative. The negative just means that the population is going down. We can't have negative population. We can't have negative percent. Okay, so we knew that we were decreasing because k was negative. We always know that. K is negative. Whatever we're measuring is decreasing. If k is positive, whatever we measure is increasing. To change that into percent, you do have to move the decimal back 2 places to the right. All right, let's do number 6. Let's do a few of these easier ones before they make us come up with what we're supposed to do. When will India's population be 1,416 million? So let's write down India's equation for its population. So we know India's population, according to this equation, is growing because k is positive. So we know if we're looking for the population, when will the population be 1,416? This is not time. They're asking you for time. So the 1,416 goes into your A. That's your ending amount, okay? We know it begins at 1,095.4 in the year 2006. We want to know when will the population be 1,416. So this time we're going to solve the equation for T. We'll be solving the equation for T. Alright, so this is where you're going to use your solving skills. We have an E, so you want to focus on your E, and you want to get your E by itself. So I'm going to kind of box it up. This is how it would look if it were by itself. Is it by itself? No. How do I get the E by itself? I divide both sides by 1,095.4. So I get 1416 divided by 1,095.4 is equal to E to the 0.014t. Okay. Now, one thing that you could do is you could try to get both sides in base E, but is that going to happen? Any way to get both sides of this equation in base E? No, E is about 2.7. It's not even a whole number, so there's no way you can get both sides in the same base. So what have we got to do to the equation if we can't get in the same base? We got to take the log of both sides. And I like to keep this in parentheses. And we're having to take the log of both sides because we can't get both sides in base E. That'll never happen. And we need to solve for a variable, and the variable is in the exponent spot. And when it's in the exponent spot and we can't get both sides in the same base, then that's when we have to take the log of both sides. That's the only way we can get our variable solved for. Now, something beautiful and wonderful is going to happen on the right-hand side, and it's going to happen in every problem in this section because all of your formulas are going to have the E in it. So on the right-hand side, ln of e to the 0.014t really says e to what power is 0.014t, and the right-hand side is going to simplify to be what? Just 0.014t. That's lovely. That means you don't have to condense. That means you don't have to drop your logs. That means that the log on the right goes completely away. And you still have that big ugly log on the left. That one's not going to go away. And now we're still solving for t. And so what's the last step? Divide by that 0.014 because it's been multiplied by your t and you want that to be all by itself. So you're going to divide by 0.014. You're going to pick up your handy-dandy calculator. You're going to do ln of that ugly fraction. You need to hit divided by. I don't think your fraction key works in this situation. You might get an error if you use the fraction key, so just do 1416 divided by 1095.4, close parentheses, divided by 0.014. We usually round our time up to a whole number. So I'm getting 18. Okay, I'm getting 18 when I punch that problem in my calculator. And they told me to begin with that T was years after 2006. So this is 18 years. And their question is when. Okay, so if they say, when did you graduate? You don't say 18 years. You give them the year. So you've got to go back and you got to take 2006 because that's what they told you. T was years after 2006. You have to add the 18 to the 2006 and then your final answer is going to be in the year 2024. That's when the population is going to be 1,416 million. Sometimes they'll ask you for years. If they ask you how old the bones are, then they just want the years. If they want to know when, they want a year. And you'll have to go back and look at your information. Okay? So those will be the easiest problems that you see, where they go ahead and give you the formulas. Alright, can you think of anything to ask? Alright, if you'll flip the page, we're going to do number 8. It's a little bit harder. 8 has an A part and a B part. We're going to start with the A part. It says in 2000, the population of Palestinians in the West Bank, Gaza Strip, and East Jerusalem was approximately 3.2 million. And by 2050, so I'm going to jot this down. So they're giving me some measurements in the year 2000, and they're giving me measurements in the year 2050. So in 2000, the population was 3.2 million. And in 2050, the population had grown, keyword, grow, so K must be positive. It has grown to 12 million. Now I'm going to finish reading the problem. Use the exponential growth model, A equals A sub O e to the kt, in which t is the number of years after 2000, because that's our beginning year, to find the growth function that models the data. So in 8a, they're wanting you to write an equation like the first 6 problems. They're wanting you to write a growth model where you can plug in any time, any population, and solve for that. Okay? So let's plug in what we know. A equals A sub O e to the kt. Do we know the original population? Yes, the original population was in 2000 and it was 3.2. Do we know the ending population? Yes, it was in 2050 and it was 12. E we know. We never substitute for E. Do we know K, the rate of growth? Because this population is growing, we can tell because the number's larger. Do we know K? No, that's what we have to find, but we do know T. How many years have passed from 2000 to 2050? 50. So we do know everything except K. So what we're going to do in the A part is we're going to just find the K, okay, and we're going to write a little formula for this specific country, for its population growth. So we have to get the E by itself, so we're going to divide both sides by 3.2. And then on the right-hand side, we'll have E to the 50K. If we're solving for K, K is in the exponent spot. There's going to be no way you can get both sides in base E, so you're going to always take the ln of both sides. And your ln of E will always cancel because ln and E have the same base. So your problems will not be, your equations will not be anywhere close to as difficult as they were last night to solve. What makes these difficult is they're just word problems, and you're going to have to just go through the word problems, write down what you know, and all that kind of good stuff. So on the right-hand side, I don't have ln of E to the 50K anymore. I just have 50K. ln of E to the 50K, the ln and the E cancel each other out, and you just get the 50K. Divide both sides by 50. And K is usually a decimal, and it's usually not pretty. Okay? So if you punch that in your calculator, what are we on? 8A. I'm getting 0.026, and you'll usually have to round here. You need to at least go to 3 decimal places. 4 decimal places is even better with your K. Okay? Now, this is what they're wanting. They're wanting you to plug this information back into the growth model. And they want it to be used over and over and over again for different informations. So the A stays there. You have to put in the beginning amount because that's where your data is coming from. The ending amount just stays as a general A, so you can use it for any problem. Your beginning amount is 3.2 million. The E stays. The K that you found, you put that in, and then the T stays. So in the A part, this is what they're wanting you to find, the growth model for this particular word problem. So they're going to give you everything to plug in except K. You go and find K, and then you plug in your A sub O, which is your original amount, and you plug in your K value, and you have your own little growth model equation for anything else that they want to ask you. All right, now the B part, they're going to ask you to use that formula. The B part says, in which year will the Palestinian population be 9 million? So you're going to use that formula that you created in the A part. So the B part says, in what year will the population be 9 million? So we get to use that formula for the B. And where does the 9 go? Into the A. That's the ending amount. We know that the beginning amount stays at 3.2. E stays in the problem. We know K is 0.026 because we found it. And then the only variable that we do not know is T. So we're going to solve for T. This equation is solved the same way over and over and over again. You use the same equation, same formula for every single problem. So you're going to divide by the 3.2 and get your E by itself. Then we're going to do what? Okay, and then I get tired of rewriting everything, so I'm going to squeeze my ln right here, if that's okay with y'all. And then what's going to happen on the right-hand side? ln and e are going to cancel. And you'll just get 0.026t on the right, and then you'll get that ln 9 divided by 3.2. And then you'll just divide both sides by 0.026. And this should give us years, and then it says when, so we'll have to add that back to 2000. So if we punch that in our calculator, anybody already got it? 30 what?
9.
39. Does it round up to 40?
Yes.
Okay. Usually your time, you go ahead and round it up. And again, they're saying when. When. So we go back to our beginning year, which was 2000, and we add that 40 to 2000, and our final answer that they're looking for is 2040.
So you wouldn't have to put some kind of...
No, no unit there. We kind of just know that's years. That is a year, excuse me, a year. Okay? Now, just to be really honest with you, that's one of the harder problems where you actually had to, you know, you had that A part where you had to find K, you had to write your own formula, and you had the B part where they gave you some more other information, you had to put it in. Okay? Now, the next section I want to look at is that little chart, 9 through 14. Charts make everything easier because they organize the information. So in 9 through 14, they've got the country in the first column, they've got the population in 2007 in the second column, projected population in 2025, and they've got the K in the last column. So let's go to number 10. The good thing is, it says, complete the table, round projected populations to 1 decimal place and values of K to 4 decimal places. So again, we're going to start with our growth model. A equals A sub O e to the KT. Bless you. So in this chart, you're just going to plug in what you know. Okay, so for Pakistan, we know that in 2007, is that beginning or ending?
Beginning.
That's beginning. Okay, so we know the beginning or the original amount was 164.7. So that goes in for my A sub O, 164.7. I do not know the population in 2025, so that's my unknown. So I don't know the A on the left. E is always in this formula. K is 0.0157. And you may think you don't know T, but you do, because this data goes from 2007 to 2025. So how many years are between 2007 and 2025? 18. So you do know time. You're going to know everything except one value. Alright, so the good thing about this one is we're solving for A. So we just have to figure out what the exponent is going to be on your E. So I would go ahead and multiply that, 0.0157 times 18. I like to go ahead and get one exponent. So that's 0.2826. Don't round until you get to the very, very end if you can help it. Don't round and then round again, because these are exponential equations and it can really throw your answer off. So then I'm going to just punch this straight into my calculator. 164.7 second ln 0.2826 close parentheses, and I'm getting 218 point some odd values. 0.5. Let's see where I worked this one out. Yeah. They said round your population to the nearest tenth. 218.5, and then this is where I do need to write million. Okay. So in the chart where I've worked number 10, they're going to give you everything that you need to know except one of those values, and then you'll just solve for that value, whatever you don't know. Okay? So that little chart should not be that bad. Let's go and look at something else that's not in the chart. Let's,
A dinosaur one?
can we do a dinosaur one? Yeah, let's see what I have written down here next. What is 14? 14's in the chart. Don't want to do that one. Alright, before we get to the dinosaur, which was 20 has to do with bones. I don't know that it's dinosaur bones. I think it's human bones. But let's look at 18, okay? Let's look at 18, because 18 describes a concept that we use a lot when we're doing word problems with growth and decay models. And we need to talk about the term half-life. And when we do number 18, it's going to help us understand what half-life is. Have y'all ever heard that in chemistry? When you're studying elements, what happens with radioactive elements? Do y'all know? They what? They explode? They can. But why are they so dangerous? They have very, very high energy, and it takes a long amount of time for that type of radioactivity to ever go completely away. So it stays in our landfills, or it stays wherever it is. We have to be very protective. Y'all know we live really close to a nuclear plant. Where's that radioactivity material kept? Y'all have any parents that work at TVA? It's in the water. It's kept not like in the river water, but it's kept in huge containers where they keep it at a certain temperature so we don't have a meltdown and we all die. The good thing about living so close to a nuclear plant is if it melts down, we're gone. Okay, we'll just be gone. We won't have to be. We'll be gone.
Just like that, or like slowly progress?
We'll probably just. I mean, it won't be a long. I mean, we'll just be gone. Okay. We won't suffer. Okay. We won't suffer. We won't. Our skin won't fall off over the last. Yeah. Okay. So, when an element is extremely strong. When an element is extremely strong, okay, it has what we call a half-life. It just means it's so powerful, it has so much energy that it takes a long time for that element to decay or go completely away. And we have to be real careful of our environment and all that kind of stuff. So number 18, it says the half-life of the radioactive element plutonium-239 is 25,000 years, okay? So that means that it takes 25,000 years for half of that element to go away. That element is extremely strong, powerful, okay? So it says if 16 grams of plutonium-239 are initially present, how many grams are present after 25,000 years? Well, after 25,000 years, if we started with 16, okay, after 25,000 years, half of that will be left. So after 25,000 years, 8 grams will be left. And then after 50,000 years, half of 8 will be left, which is 4. That's what half-life means. Okay? After 75,000 years, 2 grams will be left. After 100,000 years, 1 gram will be left, and then they want us to go all the way to 125,000 years, and then half of 1 will be left, so that means 0.5 or 1 half of a gram will be left. So will this plutonium-239 ever completely go away? No. It is an exponential decay. If we graph this, and the graph would just get closer and closer and closer and closer to the x-axis, and that value of that element would just get smaller and smaller and smaller and smaller, but it would never, ever, 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 ever go to zero. It would just approach zero. Okay? So when you're doing half-life problems, and I'm going to set up number 20, and I know I'm really close to time, but I'm going to set up number 20. We're going to use our same little formula here, A equals A sub O, but they're going to talk to us about carbon-14 dating, which is really, really cool stuff. If you don't know about it, that's how we date bones. And they're going to give us the K value. They're going to give us the K value. They're going to give it to us because it's carbon-14. So they're going to have to give us the K value there. So when we're doing half-life, okay, when we're doing half-life, we begin with 100% and then we end with 50%. Everybody listen to me? We begin with 100% and we end with 50. But in this problem, they say they dig up some bones and they find out there was 88% carbon-14 in the bones. So that means we start with an original amount of 100%. When we're living, we have 100% carbon-14. When they dug up these bones only had 88% of the carbon-14. Because when you die, the amount of carbon-14 goes away. It's 100% in you when you're living or when the object is living. So guess what we'll solve this problem for? Okay, we'll solve it for time. We're running out of time. And we've already solved here. We already know how to solve. And we'll end up with, and I thought, man, this person just got killed. You know, I'm thinking CSI. You know, it's 24, the body's 24 hours old. We end up with 1,056 years. That's how old these skeletons were. Okay? And so sometimes when you're doing one of these problems, they're wanting you to know how old the bones are. So you would just use years for that one. Okay? Homework is on the same page. You are doing, please do this homework. You're not going to be able to do these problems. You're doing 1 through 35 odd. Same page, 1 through 35 odd. What page are we on? 469. Okay? Last homework. Finish strong. Okay? Finish strong. Be successful young adults. You can do it.